right, folks, our next presenter is Brandon Badeker. Brandon Badeker graduated with a bachelor's degree in geoscience from the University of California at Santa Barbara in 2000. Working in the private sector for nearly a decade, he performed environmental analysis, downhole logging, seismic trenching, and geotechnical investigations, resulting in a professional geology and certification for geology licenses. For several years, Brandon worked for the California Department of Transportation, where he performed the design and analysis for emergency repair of roadways, retaining walls, slope failures, which involved rappelling down slopes for analysis and rock scaling, installing and removing cable nets and drapers, and testifying as an expert witness. Brandon then decided to follow his passion for economic geology, where he worked to oversee mine operations and reclamation with the California State Department of Conservation, and is now in beautiful Butte, Montana, working as a geologist for the Bureau of Land Management Minerals Program. Please welcome Brandon.
Thank you, Mike. That was a great introduction, Mike. Thank you very much. My name is Brandon Badeker. I'm a licensed professional geologist and certified engineering geologist from the state of California. You may have heard Mike mention I'm working for the Bureau of Land Management out of the Butte field office, and a lot of you old timers are going, well, hey, that's Dave Williams' spot. Dave was with the BLM for 42 years, retired just a few years before I got there. And I see his work daily, reviewing old reports and from these mine sites, and I really just want to acknowledge Dave's work for the mining community, for the taxpayer, for the local community, all the work he did cleaning up AML sites. With Joan Gableman, I got a chance to work with Joan. Unfortunately, she doesn't look to be here this year, but a lot of you guys know her as well. She is really, honestly, one of the smartest, hardworking geologists, both of them I have ever met, and I really just wanted to acknowledge them at the beginning of the talk here. In addition, I'm a geologist. I'm not a computer guy. I'm not a 3D modeler. I'm not a 3D practitioner. And as Mike had mentioned, I used to do a lot of emergency repair of infrastructure, roadways, and that's kind of where this came about. I needed a tool that I could kind of measure volumetric areas in a straightforward manner without, say, using a tape measure. I'll go into a little bit right now. One of the first projects that came about was some voids under a roadway. I did ground penetrating radar, drilled holes, dropped cameras down the holes, and just found hummocky void spaces. Bridge engineer looked at me and said, how on earth are we going to measure this volume? I said, well, I don't know. I'm going to figure it out. In the middle of building the downhole camera, I also wanted to know, again, how far was I looking at? And I was lucky enough that the industry was just starting to come about with this 3D technology. So, and again, a lot of us aren't 3D people, but we've seen a lot of talks this year, probably a good 25–30% that have had 3D data in them. So the industry is moving real quickly, and I see a lot of people are still stagnated. They still got this sense of, I need a $50,000 LiDAR in their heads. Well, while we've all been kind of pigeonholed in our jobs doing what we do best, this whole other industry has been exploding. And these are, sensors or measuring devices that will give us 3D data for use in, multiple applications. And it'll be you guys that'll determine the application that best suits you. So I don't want you guys to, be scared at this new 3D world. I'm going to be doing a little crash course here to just start from the basics for you guys that are, maybe just completely overwhelmed with all this. This is going to be super easy and hopefully nice and fun for the last talk of the show. So that being said, let's move. So what's a point, right? Point simple. It's something we can measure. Usually, oftentimes we use a tape measure or something like that. But in this case, in the 3D world, we're in XYZ space. So we'll take, like the corner of the podium or something like that. We could stand over it, at a reference point, use tape measure. We could plot that on a piece of paper if we wanted to. Not a big deal. So all we're doing is with the computer. So we hear point clouds a lot. What the heck's a point cloud? I have really no clue. Well, if I was going to stand over on the side and take a tape measure and measure all these points, I could get 1,000 points on here. And if I'm going to graph that on a piece of paper, there's going to be a series of points. Well, that's essentially all point cloud is. They really come in this is raw data. It'll take just a second, I think, to pop up. It should be thinking. So this is a point cloud. I mean, I've got probably 1 million points in here. Now, when we start getting enough points, we can start defining geometries, start defining maybe textures. In the case of the device I use, which I'll get into in a few, and I won't recommend actually using it because there's better systems now. I get a color point with each of my XYZ points, and so I can identify colors, textures of the geologic materials I may be interested in. So this is the raw data. That it's not really going to help us much. The computers don't want to assess anything as just a series of points. So we have to kind of step a little further, and what we're going to do is we're going to create now a surface off these points. So that's what we call a mesh. These are created from algorithms from really smart guys, mathematicians who are sitting in corners, and essentially just connecting the dots. So I got a dot here, I'll connect it with an edge. Dot there at the bottom, dot there at the bottom, connect it with an edge. Again, we got a face. So you can see kind of on the side here, my little background photo, all these little lines, and these are the connect the dots, if you will. And we call those edges, and in between the edges, we'll have faces. Well, now that allows the computers to more happily say, well, we've defined a volume now for the computer to be able to analyze. And again, there's too many algorithms to list out there. There's, depending on how they measure each point and other points, they can be very complex or very, very simple. A lot of people remember the old term of like a 10 mesh. Everybody used to call them 10 meshes. 10 meshes. Those were trigonal. We don't always use those now. We use poly meshes, polygonal meshes. So these little areas in between all these little dots, all these lines, they used to be triangles, and that's not always the case anymore. So we just, if you want to sound like the cool kid, it's just a 3D mesh, Mesh Lab, bottom here, is real good open source software for creating meshes out of point clouds. I'm gonna go into open source a little bit in the next couple of clips. But this is a program you could download. You could, you could leave here today, not buy any equipment, and start getting into the 3D world. There's been LiDAR flown all over the place, and you could download that. You can, download one of these open source programs, not pay a dime, and start getting into it. So here's a mesh. This is going to be the same kind of general area that you saw the point cloud. But in this case, all the points are now connected with the surface, line surface. It's hard to see, but it's almost like a photograph in essence. I have a solid surface. All this white down here, that was data loss. I use an infrared system in this case. And as you saw earlier in Brant's presentation, all these systems are going to have limitations. And water, anytime you're trying to measure something with a camera of any sort, or laser, infrared, some light, EM light source, that water's going to, disperse it, and you're going to not be able to collect good data there. You're going to have to look at the application you want to use it in, really. So again, kind of cool. We can get the geometries, textures, all from just 3D point data. And we're not sitting there with a measuring tape, measuring. I mean, that's why we invented the computers, right? Is to make our jobs easier. So theoretically, this kind of does. So last bit of basics of 3D terminology. Again, I want to get in that open source. This is software that's developed to maintain more for societal interest or developer interest than it is for a profit. You can donate to these developers. That's fine. There's nothing wrong with that, but that is not why this software is out there. And this software covers the whole gamut of proprietary software out there. And I know some of you guys are going to hate me, but anyway, so document creation and editing, we use Microsoft Office, right? Well, there's OpenOffice out there. And these files transfer, to the Microsoft world, DocX, and photography, I think everybody knows Photoshop. Well, the open source version is GIMP. And I think that's a new image manipulation program. GNU is a essentially open source licensing software that has tons of libraries. And so if you start getting an open source world, you'll start seeing GNU or GNU quite a bit. GIS, the Esri suite, most of us got to know the Esri suite. I'll get on my soapbox a little bit again because GIS was created with taxpayer funding. By the government, USGS, NOAA, a couple other agencies involved. And those libraries and all that functionality is available without that $3,000 licensing fee. And it works great. I run QGIS at home, layer in all kinds of old maps and data for personal projects. 3D animation software, Disney's Pixar, they make all these movies that these kids love. They've been doing it for decades now. They use a program called Maya, very expensive. Open source version is Blender. That's actually the program I use to do all my animations in here. Even though it's open source, as you say, it's free, these aren't necessarily simple pieces of software. I've been running Blender for 10 years, and I still consider myself a newbie at it. So they're very competent pieces of software as well. Funny thing with Blender, I've actually run fluid and rockfall simulations on them as well because it has a full physics engine. Now, before we get too heavy into this, with anything in life, we got to remember that 3 constraint triangle, right? Speed, cost, and quality. We can only have 2 of those. This talk is cost-effective techniques. So I'm reducing my cost, so I'm gonna have to bite it in the rear some other way, quality or speed. Generally with 3D, it's gonna be speed with post-processing. Again, we're getting that raw data either from our very expensive flown LiDAR or even from direct measurements. Now putting those pieces together into a digital surface is gonna take time. Luckily, the industry has improved dramatically, and I'll give you a couple programs that may help speed up that time. So file types, what kind of file types you can get into? Point clouds, again, these are usually for raw, pre-processed data. XYZs, .las, common in our LiDAR data. .plies, Stanford polygonal file formats, that's usually what I'm using. The XYZ is an ACSI file format. It's binary. It's very basic. It's a number, comma. It's a comma delimited, so you can change it in Word, Notepad, or Excel. And 10 years ago, we had to. These programs didn't talk very well to each other, and so we were always in there changing kind of header files to change the file formats. And I know Brant mentioned this morning that it's still a problem for some of these programs, but it's gotten a lot better, I'll tell you what. Most of these programs can import or export any of these kind of file formats. So after we do a mesh, we've created these points into a surface now, dealing with objects, wavefront files, STLs, and .dwgs. A lot of people know .dwgs from the AutoCAD world. AutoCAD is probably one of the first companies that really brought 3D back into the industry and knew people were going to be working with it. They got their programs, they got their software down. And I really can't say there's an open source version of AutoCAD that works nearly as well. That's one of the few exceptions. So now methods, this is techniques, not just one technique. This is not what I did. There's multiple ways to do this. And visible light is one of the ways. Our eyes use visible light. We got 2 of them. It's either emission from light into our eyes that we can see 3D, or even you can use a narrow beam of light. Research back about 10 years ago or so was pretty rudimentary, but the evolution of that has come quite a ways. Laser, we can use that same narrow beam of light, and I'll go through these a little bit more in a sec. These laser can be done in narrow beam as well, and through a process of interference with a solid substance, you get essentially a change in that beam of line. That's one way laser can do it. Another way is LiDAR, and these are kind of individual hits. LiDAR shoots out a laser, brings it back, times it, and that's how it gets its range. And a LiDAR is going to do that. It could do it thousands of times a second, depending on the system you got. Photogrammetry, again, big boom in the modern world with the UAVs. But photogrammetry is really there to mimic our human eyes. We see in stereo vision, providing more than one image. We've done that for 100 years as geo-practitioners with stereoscopes. This just brings it into the virtual or digital world. The great thing about photogrammetry is, again, exploded. There's abundant hardware and software out there. And I'll give you guys a couple tools by the end that you guys could leave here and start just scanning stuff. Infrared is similar to LiDAR. It uses a display of points to map a scene or an area. These are not just one device, they're a range of devices, from little robotic eyes, if you will, to even game controllers. Use these infrareds to essentially map out a surface. Who has one of those little robot vacuums? Well, if it's got obstacle avoidance, it's probably got a little infrared sensor in there that detects the range, and when it hits something, it says, oh, there's something there, changes direction. So these things are very abundant at this point, and super good for us if we like messing around and coming up with new tools to help do our job. So we'll go back in here to visible light. Again, narrow beam of visible light passed over a surface will conform to the depth variances on that surface through light surface interference. Edge detection algorithm is then performed on the photograph. Imagine you're going to have a black screen and a single line. Well, actually, we're going to skip to the next one here real quick and show you. I should have done this first. So this is what a narrow beam of light, i.e. or laser, will do as well. It'll conform to a solid object. The lines will. Well, I think a lot of us have done this, just through messing around with flashlights in dark rooms as kids. And so people ran with this quite a bit. And generally you run an edge detection algorithm on that light beam, and you keep pasting that together, and you'll have a scene digitally. So the interferometry, white light interferometry, is really blown up as well. I was really shocked when I first started looking at this. It was very rudimentary, and wasn't sure, really how to apply it easily. But luckily now and I'll show you in a sec, there's little handheld scanners that'll scan to a millimeter or less accuracy. You increase the cost, the smaller scale it can go. These will work for small and large scales. A lot of them are doing it on the nano scale at this point, and it really surprised me. So let's see, we saw that. So here's just a general search page, not anybody in particular. You can go onto Google or whatnot and type in white light scanners, and you get these little handheld scanners all over the place. And we're talking, these are in the orders of hundreds of dollars, not thousands of dollars. And I implore you to actually go watch the videos. I didn't want to steal anybody else's thunder off of YouTube or anything like that. And but the intricate scale that these things can scan at anymore, and so quick, it's just absolutely amazing. Blew me out of the water, and it might be the way I start looking at in the future if I keep messing with this. So laser, again, laser line interferometry is similar visible light. We have laser rangefinders all over the place, right? And we could actually do that, plot it out even on a computer. Just take our AutoCAD and start bink, 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 bink. And that's going to take a while. We really want to do that? Probably not. So LiDAR detection and ranging. Now, LiDAR is really what we typically think of when we're discussing laser in 3D, but there are, again, other methods that interferometry, where you're using a laser beam, and then individual laser hits. So there's 3 different methods that you're kind of using. Kind of funny, I was actually thinking about building a device that used a laser beam. And then I was at a talk a number of years ago. It was for highway geology. And sure enough, Golder and Associates had already built it. So I said, okay, well, I'm done. So the cost and availability of these systems have come down considerably. Again, your $50,000 LiDAR they're there and they're applicable for certain things, but for small scale projects, probably not the way to go about it. Here's again another little search on some of these LiDAR systems. And we're talking hundreds of dollars. How many people have a Tesla or a self-parking car? All these systems are now being put in there for those cars to be able to do that. And so the price has just come down. Come down to the point of really a hobby level. When I've got 3 kids, so that sucks all my money. I really had no money to develop anything, I do here I was about to show you. So, I mean, this is looking good. If we can get sensors on the order of, hundreds of dollars instead of thousands of dollars, then we can start utilizing these systems for applications in the geosciences where we didn't in the past without having to hire a consultant or a contractor. I had a colleague, this area is blowing up so much. We're working in our little narrow niche, so we don't see this industry just taking off. And so my colleague, Dan, who's with BLM, Dan Seifert, he's like, hey, well, have you seen this Cavatron system? I said, no. And well, this is a do-it-yourself, open source LiDAR system that they're using to map caves. Now, looks real cool. Not very expensive given the sensors that are out there. The only limitation I see with this is it doesn't really give you a color point with your 3D point. So you're getting what you're going to end up with is a gray mesh. It's good for volumetrics. Not so good for coming back in there and say looking at the geology in the mine, but that's solvable in the 3D world. We call them a material. You can take a digital image and you can superimpose it on there. Photogrammetry uses photographs, videos, and any multiple, some are proprietary algorithms to stitch photographs together in a 3D volume. I think it was, people are really liking the Autodesk algorithms. Apparently they're pretty darn accurate because typically the photogrammetry is going to give us less accuracy or less precision. It's very accurate, it's not precise, I'll say, than these other systems. But because of the use of the UAVs, again, it's absolutely blown up. And here I have a little diagram of what it does. Again, we have a moving image of some kind, whether it's video or static, and the computer is placing these points together into a 3D volume. Open source software for this apparently is Meshroom. It's real good. You can go out and take pictures, upload them in there, and it'll start stitching them together. It'll spit you out a point cloud or even a mesh that you can go and then manipulate in other software to do what you need. Whether it's you're building a part, whether you're doing a flood analysis, 3D's coming along so that you're going to be able to find applications for what you're doing, and to utilize these systems. And at the very least, even if you don't, you're going to start being more familiar with seeing this stuff come through the door and utilizing these systems. So I implore you, again, open source, Meshroom, mess around with it. Again, Autodesk was one of the foremost in all this. They used to have a free software online. It was called like Autodesk 4D or something like that. And you used to be able to upload your photos into it and it would stitch them together. Well, Trimble bought that and it was no longer free, so I stopped using that. And so here's a little culvert scour I did just for kicks and giggles a long time ago using that Autodesk program and some other open source software. So you can see we are getting some 3D geometry in there. And it's just static photographs. And this was actually pretty dang old, and this is a new one. This is done over a smartphone using the Polycam app, and they give you 3 free trials, and then it costs money, but it's $80 a year. That's not very much compared to your $3,000 Esri license or your AutoCAD license, and the accuracy is getting better and better and better. So you can see how precise this thing is. And that was just simple cell phone. So again, you want to talk cost efficiency, we got the hardware in our pocket already. So infrared uses a colored point cloud with ransack or slam algorithm. You may hear people go, I'm going to come and I'm going to slam it. Essentially, that's just an algorithm to make a mesh out of a point cloud. And it's a little device. Multiple devices will do this. And so that's pretty much what they're doing. They're doing infrared scanning, usually. And so rangefinders, small robotic sensors, again, even game controllers. All my scans in here, I actually used an Microsoft Xbox Connect. And I don't know if you guys remember, because it's getting kind of old now, but it turned you into the game controller. You didn't need to hold a controller. And so the guy who invented it for Microsoft was an absolute genius, but Microsoft didn't know what they had until it got opened up. When I was sitting there looking to build a downhole camera and need to know how far I was going, that was a perfect time because the hacking community had paid some guy to break into this thing and figure out how it worked. So I said, well, that's exactly what I need. So I glommed onto that system. But once they did that, Xbox figured out what they had. Essentially, it spins out a splay of infrared points in a known configuration. And anytime those points come back to the sensor and they're deviated, it provides a surface to it. Genius. In addition to that, though, they also did skeletal trackers in there. So when it got broken open, people started using them for scanner and everything. And actually, people were starting to use them for physical therapy, too, because it had these skeletal trackers. And so the world kind of opened up. Microsoft realized what they had, so they started selling the sensor separately. So for like $200, you could buy the sensor, hook it up to your computer, and then they add some software that you can mess around with as well. Now they have a version 2. That's why I'd say don't go with the one I used, although it has upwards of a 2 millimeter accuracy. They have new ones now with more accuracy and higher resolution. So you want to go looking that route. Microsoft actually has sensors, and there are other proprietary infrared sensors on the market that are more standalone. You don't have to necessarily cobble together some robotic infrared sensors onto an Arduino board and figure out how to program it. Now it's been done. So the Cavatron, using a system like that, looking out there for some of these other open source software, you'll be able to piece this stuff together and do it a heck of a lot easier than, say, I was doing it. Here's a small scan from an underground mine that I did with my Connect. And you can see all the points. I actually grabbed 20 million points within 10 horizontal feet. Now, my problem is post-processing. I only get like 10-foot scans, and I had to put them together. There's automated processes now to do that. And so, what was not necessarily feasible early on is now feasible. I think I've told a couple of people, I actually, the hardware, all the hardware alone was, $2,000. And most of that was a gaming laptop, so I could carry it under there with me and have it do some of the processing. Anymore, the way the industry has gone, you could be collecting that data generally in your hand and then coming back out and running it. I would still recommend a pretty high-end computer because when you're dealing with 3D data, it's voluminous. I've got a colored mesh scan of this as well, and it's about 1.5 gig file size alone. So you're just going to want some with a bunch of RAM that can handle some of this. And one of the things is to think about your application because in this case, and if I have some time here at the end, I'll show you another video, shadowing effect. You got to look at the direction you're scanning. So I'm going to come back through here. See, this looks nice, a lot of filled in holes, or no holes, excuse me, they're all filled in for the most part, even though I've just got points, right? But now I'm going to come backwards and see, I didn't scan that direction. So essentially it's shadow effect. So you're going to think about your application too. Are you going to need to go forward and backwards? Is the time going to make it, not efficient for you? Oh, dang it. Wow, that was fast. So hardware, inexpensive digital cameras to standalone systems can be obtained for relatively little cost. Again, we got our cell phones in our back pockets. So we already have half the software. Each system will have its drawbacks: accuracy, post-processing time, or cost. Software, open source software that you could go download and run with. Blender, MeshLab, Meshroom. Matterport was another one given to me by Iljad. And this does automatic stitching for you as well. These will accept a phone camera, or you can use other devices. And I think he was telling me their scanner that they were using at their company cost $5,000. So you're talking $50,000 LiDAR, right? No, now we're at $5,000. And his scanner is more standalone. So you don't have to sit there and really mess with half of it. You're already in that world, and you're only into it for $5,000. That was still too rich for my blood, but some of you guys may be able to afford that. Pros and cons. So utilizing expensive LiDAR should only be applied to large scale, as modeling smaller scale objects can be performed with cheaper hardware or other methods. So yeah, don't necessarily go out and buy that $50,000 LiDAR if you've got a small project. They're very applicable for big projects. You wouldn't want to do this on the Berkeley site, or flying. There's a reason that we're putting LiDAR on planes, helicopters, UAVs, because these will handle a large area well. Now, maybe you do that and you get a contract, you have your LiDAR flown. Now you got that 3D model. If you have small things to add to it, now you can use your own device. You don't necessarily have to hire the consultant to come in with his expensive equipment. Photogrammetric methods are best applied for simple, not intricate structures where accuracy can be reduced, like stockpiles, buildings. That's changing rapidly. They are getting far more accurate. I mean, you're using I think it was brand 70 or 42 megapixel camera. So you got lots of points to be able to get together. Open source software can be buggy. Use stable versions, or if you absolutely have to, a proprietary software. Finding hardware software suite can be time consuming. Do your research, go online, go on YouTube, type in 3D scanning, find out what other people are doing. Maybe that's applicable to what you want to do, and you can run with their system. See, I'm not here necessarily just to give you a system, because there's so much out there, and not any one system is going to be applicable for any one need. So go out there, do the research, because that industry is booming, and we can use it for geologic practitioning at this point. So post-processing can involve a large learning curve, and you may want to avoid that if you're using it as a tool in your job. Volumetrics, why? Why do we want to do this? I can do it all on a piece of paper. Minimum, maximum size determination for tunneling or mining equipment. Yes, we can go in there, bearing, shoot, do all that. Are we getting necessarily all our metrics off of our tunnels? No. So we can quickly go in there and do minimum, maximum widths, heights, see if there's equipment issues. We can do volumetric estimates as excavation, air volume. Now, typically in the past, we've done just a geometric approach with a factor of safety. Nothing wrong with that. But if we're in there doing it, we can get these other values as well. We can create plan sets, plan and profile views. And so there is applicability. And when I look at one of the first topics on that BIM model, it really seems like this is going to be a great way to go for for collaborating in the future. Geologic evaluation, I'm just hitting on a couple points. I've already been thinking of things as I've been sitting here watching talks as well. You can combine it with fracture evaluation software to assess the kinematics and safety of rock structures, either slopes or tunnels. Perform geologic evaluation without having a continuous presence in that mine. For unsafe mines, you may not want to go in there a bunch. You may not have the ability to go in there a bunch. So grabbing as much data as you can while you're in there, not just a picture, not just a video, but actually geometric data, you may want to do that. You can add to other data sets to creation of, like, say, ore body models or other geologic investigations. Multiple data sets can be combined, kind of like GIS, if you will, layers. You can combine them all to give you a whole lot of different information from different sources. So I think that's it, and I think I'm pretty much out of time. If you have any questions.
Thank you, Brandon. We have any questions for Brandon?
Nope.
Looks like we're hungry, or lunch is right around the corner or something. Well, with no questions, thank you very much, Brandon.
Hope it helped.
And with that,
Okay, cool, thanks.